Welcome back. So, in today's video lecture, we will look at the hydrophile lipophile balance HLB guideline, and we'll also look at the Debye plot, right? And after discussion about these two topics, we will also look at the tutorial section. We will try to solve problem on the aggregation number, right, and the critical packing factor, right, and we can comment based on the critical packing factor that we found from the problem. So now let's begin. Okay. Yeah. So so today we will look at, in this lecture we will look at the hydrophile lipophile balance, which is also called as HLB number. So this guideline will be very much useful when you want to stabilize, let's say, uh, oil in water emulsion. Sometime you may be interested in stabilizing water in oil emulsion. So what decides the type of emulsion, whether it is oil in water or water in oil? What decides the type of emulsion, right? So as you know, the surfactant is amphiphile compound, okay, which consists of both hydrophilic and hydrophobic groups. So sometimes hydrophobic groups may be more dominant, okay, than hydrophilic groups. Uh, so in such case, you know, the surfactant, the given surfactant will stabilize uh, water in oil emulsion. So in such case, they would try to maximize their exposure with the oil, right? Because they would like to maximize their the contact with the oil, like oil, oil phase, right? In such case, you can expect that they will stabilize water in oil emulsion, right? So uh, alternatively, sometime you might deal with surfactant, which is more of hydrophilic, in nature. So they may be more hydrophilic in nature. In such case, you can expect that they will stabilize oil in water emulsion. So in these cases, the continuous phase will be the one in which emulsifier will be most soluble. Okay. Let's say if it is water in oil, you can say that the emulsifier is most soluble in oil phase, right? So that actually comes from the Bancroft rule, which says that if continuous phase will be the one in which emulsifier will be most soluble. Okay. Alternatively, you can also say that most surfactant which is more which is most water soluble should stabilize oil in water emulsion, and the one which is oil soluble, most oil soluble, will should stabilize water in oil emulsion, right? So now the question is, what is the use of the HLB guideline? So Griffin actually developed this HLB guideline, which is same as something like pH scale, right? So you got a pH scale where you have the number from 1 to 7 and then up to 14. So you know that less than 7 and uh, how the pH will be when it is less than 7, and how it will behave when it is greater than 7. Similar way, Griffin has developed HLB scale, okay, between 0 to 20, okay. uh, so it means that when it is very close to 0, which means that it is completely lipophilic, or you can say hydrophobic. When it is completely 20, when it is 20, you can say that it is completely hydrophilic, right? So in between, so they will actually bring a mix of, or the combination of both hydrophobic and hydrophilic. Okay. So what Griffin has done is he has tabulated a range of HLB, okay, for different applications. Like for example, if the HLB range of a given surfactant is, let's say, 4 to 6, in such case you can say that this particular surfactant will stabilize most likely water in oil emulsion, or you can say the emulsion that will be formed out of this the action of the, I mean, out of the surfactant that we used, I mean, the particular surfactant that we used to stabilize emulsion will result in water in oil type emulsion. Okay. On the other hand, between 8 to 18, you can say for sure that they will stabilize oil in water emulsion. Okay. And wetting agents will be somewhere between 7 to 9. Detergents will be somewhere between 13 to 15. Similar way, solubilizing agents will be somewhere between 15 to 18. So depending on this range, one can actually use the surfactant. I mean, one can predict the type of emulsion or type of dispersion, or where the surfactant can be applied. Okay, right. So that is the idea. Uh, so if you want to calculate the HLB guideline, one has to use this scale, which is proposed by the Griffin. Uh, so for this is applicable for mostly for non-ionic surfactant. Okay, and so this MH represent molecular weight of hydrophilic group. Okay, and the M represents molecular weight of the whole molecule. Okay, so this multiplication factor 20 is used, so that whatever you calculate is integer, between 0 to 20. Okay, a value between 0 to 20. Okay, so this is a simple rule saying that if HLB is greater than 10, they will be mostly they will be water soluble, or they will be uh, mostly water soluble, uh, or you can say hydrophilic is more dominant character. If it is less than 10, you can say hydrophobic is more dominant character. So I have given one example for you to do this exercise. Uh, so maybe, I mean, I will show the answer also at the bottom. So you can see that this is actually the mono-oleic acid ester type of non-ionic surfactant. Okay, here you can identify that this ethylene oxide is the hydrophilic group, and the rest is the backbone, which is hydrophobic groups. So we know that the hydrophilic, so the molecular weight of hydrophilic will be uh, based on the ethylene oxide, one has to calculate, and the molecular weight of the total compound is 671. If you calculate that, the HLB number that one would get out of this calculation will be 11.8. Okay, so if you look at this 11.8 in the table, it is somewhere between the second one, that is oil in water emulsifier. So you can say that this particular surfactant, that is mono-oleic acid ester, will be when you use this as a emulsifier, this will most likely stabilize oil in water emulsion. A type of emulsion that one will be obtaining is oil in water emulsion. So that is the idea, right? So next we will look at the Debye plot. Okay, if you look at the Debye plot, it is basically obtained from the uh, uh, light scattering data. With the help of light scattering instrument, one can obtain this data. So when you plot the Debye plot, when you use this Debye plot and plot this, the concentration on the x-axis, and uh, this whole parameter on the y-axis, you would get a straight line, and the slope of that will be a second virial coefficient, which is 2b, right, in this case, and the intercept of that will be the 1 by m. So m is the molecular weight, right? So this is actually proposed by Debye, and this is often popularly called as d by plot. Okay, so this you can obtain from the light scattering data, and this h is actually the constant which is function of the refractive index and wavelength Avogadro number. This quantity, that is dn by dc, one can obtain if you construct the graph between n versus concentration. The slope of that will be dn by dc, right? That you can actually use, that data can be used here, and this entire data can be obtained from the manufacturer, right? uh, Maybe when we operate the particular light scattering instrument, these data can be easily avoided. And when you plot them on the y-axis, so basically the c and tau will be varying depending on the concentration of the sample that you will be subjecting to. So based on that, you will get the different y-axis and different y value and different x value. When you plot them in this fashion, you will get that the straight line will be formed, and slope of the line will give you the second virial coefficient. Although what is important for us in this plot is the intercept, right? So one can actually calculate what is the intercept from this data, and that can be obtained, that can be used to calculate what is the molecular weight of the micelle, right? So when you so this molecular weight of this micelle uh, can be imagined as the size of the micelle itself, right? When you divide this molecular weight data with respect to the molecular weight of the individual compound, that is the CTAP type surfactant, right, which we have used, and which for which the data has been produced, right? So you can use this CTAP, I mean molecular weight of this CTAP surfactant, that is nothing but 308. So when you divide this number with the molecular weight of the CTAP, so one would get the aggregation number. Okay, so this actually implies that the number of monomers which are used to made up of, which are used to uh, making the micelles, right? So you can understand that this aggregation number is coming from the data that we obtained from the scattering, right? So once we know the aggregation number, it is easy for us to calculate for example the packing factor, right, sometime, right? Then one can comment on whether the micelle that will be formed is spherical, cylindrical, uh, or the any appropriate shape, right? Right. So now based on this information, we can try to do this tutorial. We can try to solve this problem. So in this exercise, what is being asked is, so the aggregation number of this SDS micelle is given. Okay, now you have to calculate the packing parameter and predict the shape of the SDS micelles. So in this case, shape is not given. So maybe what we have to do is we have to calculate what is the V by A into L max, right? So this is something one has to calculate. So once we know this value, you can comment on the shape of the micelles, right? So that is the idea. So remember, we know what is the Tanford equation which we saw in the previous lecture, right? So this equation is a empirical equation which is used to calculate what is V and what is L max, right? So this is actually function of the number of carbon atoms. Okay, as you can recollect, so this V and L max can be calculated based on the number of carbon atoms, because here the carbon atoms for this case is 12. one can use this equation, that is V equal to that is V equal to 0.0274 plus 0.0269 n. So when you calculate this, you would get 0.3502 nanometer cube, and the L max is nothing but L max is nothing but 0.154 plus 0.1265 n, right? So this is nothing but 1.672 nanometer. So these two values we know. Now what we need to do is we need to substitute. Let's say if we assume that the spherical will be the micelle, the shape of the micelle will be spherical, then the volume is going to be 4 by 3 pi r cube. Okay, so which means that the n is nothing but 4 by 3 pi r cube divided by volume, right? Volume of individual surfactant. So since we know the n, that is 80, and since we know the n and v as well, what we can calculate is the r, radius of the micelle in this case, right? So if the radius of the micelle we can calculate, and the radius of the micelle will be uh, so 3 into v, right? 3 into v uh, divided by into n, right? 3v into n divided by 4 pi power 1 by 3. So this is nothing but uh, so the radius here is 1.884 nanometer, right? Yeah. So then once we know the radius of the micelle, you can calculate what is the A, which is nothing but 4 pi r square by n. So actually n is nothing but 4 pi r square by A, which is the optimum head group area, right? So you can actually calculate A because we know what is the aggregation number as well, and radius as well. So A in this case will be 0.558 nanometer square. Okay, all right. So we know this data. So by knowing this data, what we can calculate is what is the V by, so what is the V by A into L max, which is nothing but we already calculated V is 0.3502 divided by A is 0.558 into L max we calculated, that is 1.672. So when you calculate this V by A L max, right, based on the Tanford equation, you can actually calculate V by A into L as 0.375. Okay, if you look at this packing parameter, which is V by AL for this problem, it is nothing but 0.375. Remember, for micelle to be spherical in shape, it has to be less than or equal to 0.33, right, or 1 by 3, right, or 1 by 3. But if you look at the value of the packing parameter that we calculated for this case, right, based on the aggregation number and the Tanford equation, is nothing but 0.375, but 0.375 is little more than the 0.33. Hence we can say that the shape of micelle uh, shape of the micelle will be non-spherical, will be somewhat non-spherical to some extent, right? So it will not be perfectly spherical. So that is the observation that we can make, out of this exercise. Okay, we will stop here. We will continue from the next lecture. Thank you.